attention.
Yes.
Okay? You do not need anything else today besides that handout that you got from the cubby, which is a set of guided notes and a practice worksheet that goes along with Unit 4, Module 4, 4 colored pencils, and a black and white periodic table. And I'm talking about the black and white periodic tables that you guys were supposed to pick up from the cubby last class period. We noticed in last class that a lot of people left those behind. We found a lot of them sitting on desks. So if you do not still have that, we did still have some on top of the cubby, so please grab one of those and remember what I said about the colored pencils? They need to be 4 very different colors. So you don't want like 4 different shades of blue, you know, or 3 different shades of orange, that kind of thing. It has to be 4 different colors, and you'll understand why later, okay? So, first thing we need to talk about is the Unit 4 test. So we talked about at the beginning of last class period. This class actually took a little poll everywhere to try to decide what we were going to do with respect to the Unit 4 test because the B-Day class periods are getting a little bit behind the A-Day class periods and won't catch up until the end of the week after Thanksgiving. And so what that means is you guys are not ready for your test and will not be ready for your test next Tuesday, all right, because it's not the same sort of numbered class period as the A-Day on Monday, all right? And what that means that you're not really ready for that test until after the Thanksgiving break. So we had taken a little poll everywhere to sort of figure out whether you guys wanted to have the test on Tuesday or whether you wanted to have the test on Thursday. And you guys had voted, it was 60-40 was the split. Y'all had voted to have the test on Tuesday, all right? Well, then I was in a meeting at lunch, a department meeting at lunch on Tuesday, and a couple of administrators were present, and we were talking about the sort of no homework over break policy. And I talked about the fact that my students had voted to take a test on Tuesday after break. And I was told directly that they did not want that to happen. And they said that that requires that students study over break. And I argued that no, it does not. And I said, students do not, and I would tell them do not study over break, but instead just review on Monday night prior to the test because Monday is a school day. They said that students will feel compelled to study over the Thanksgiving break, and therefore I simply should not schedule the test for Tuesday after break. Okay? So, that is basically telling me I have no choice. All right? I can't give the test next Tuesday. We're not going to be ready for it. Okay? We're still going to be wrapping up the unit next Tuesday. All right? And I can't give it Tuesday after Thanksgiving break, which means our only option then is for Thursday after break. Now, when we were having this discussion on Tuesday, I do need everybody quiet and paying attention. When we had this discussion on Tuesday, I believe that it was Jackson that had made an alternate suggestion, correct me if I'm wrong, but Jackson had said, because my original plan was that if we took the test on Thursday, that next Tuesday we would wrap up the content, we would do the comprehensive review. The following Tuesday, after Thanksgiving break, that we would start with the Unit 5 material, and then on Thursday we would take the test. I believe what Jackson offered as the alternative suggestion was, what if we start Unit 5 on Tuesday of next week, meaning before Thanksgiving, am I right? And then Tuesday after Thanksgiving would be the day that we would wrap up and review Unit 4, and then on Thursday we would take the Unit 4 test, okay? I didn't want to say yes to that until I got to speak with my co-teacher, because Ms. Smith and I do all of our planning together, and we try to keep our courses on the same pace and following the same pacing guide and curriculum map and all that other stuff. So I've spoken to her, and we do feel that we will be able to pull together the first module for Unit 5 by next Tuesday. And therefore, if y'all are okay with this, my new plan would be that next Tuesday we actually start Unit 5, okay? The Tuesday after we come back from winter break, we would do our Unit 4 review. And then the Thursday after Thanksgiving break, not winter break, excuse me, but then the Thursday afterwards, then we would take the test. Does that make sense? Okay. Are we okay with this sort of scenario? It's kind of the only one I'm left with. I mean, It's either that or we go back to, we wrap up the unit on Tuesday, we do the Unit 5 on Tuesday coming back, and then we do the test on Thursday. Okay? So, are we good with that?
Yes, ma'am. Yes.
Yes? So is that what we prefer?
Yes.
So that the Tuesday immediately before the test, that is review day. Okay, all right, so that's what we'll do. So next Tuesday, we'll start Unit 5. The following Tuesday, we'll do review. And then Thursday, after Thanksgiving, we'll take the test. Okay? All right, so that's out of the way. Unit 4 test has been rescheduled. So then today, you guys, what we're going to do is we're going to work on Unit 4, Module 4. We started that on Tuesday when we did the POGL, when we did the electron configuration POGL. And we did all of the discussions about the boarding house and the orbital diagrams and those types of things. Okay, that was our introduction to Module 4. So today what I'm going to be doing is I'm going to be lecturing from the Module 4 PowerPoint, and that PowerPoint is available on Schoology. All right, so I'll be lecturing from that. It's going to be over there on the Promethean board. All right, but I'll be coming back up here to this board to be writing out things as well. And I'm going to constantly, as we're going through the Module 4 PowerPoint, I'm constantly going to be referring back to the activity that we did on Tuesday and tying all of the pieces together so that you understand how it all fits together. Does that make sense? So that's our goal today. All right, so what I've given you is, and this is not sort of my customary thing to do, but I've given you guys a set of guided notes to go along with the PowerPoint so that I can make sure that you guys write down the most important things, okay? If at any time as I'm going through the PowerPoint, you feel like, you know, sometimes people are like, wait a minute, can you go back to this slide so that I can just write down one more thing? I don't mind if that's for just a second, but please remember, where can you find the PowerPoint if you miss something?
Schoology.
It's on Schoology. So you've always got that as your backup plan, okay? So if I have to keep moving, just remember, go to Schoology, it's all there, okay? And don't stress about it, all right? Just fill it in after the fact. Okay, so you guys, it is not very often, and I hope you would agree, it is not often that I stand up here and lecture for an entire period. Would y'all agree?
Yep.
Okay? We try to make this as much of an interactive and sort of hands-on experience as possible. But for what we're doing right now, I have to stand up and lecture. Okay? So my feet and my voice get tired at the end of the day. Yesterday I was exhausted because I did this lecture 3 periods in a row. And my feet were killing me because I didn't wear the right shoes yesterday. All right? But I wore more comfortable shoes today. So hopefully I'll still be standing and I won't have, you know, a froggy voice at the end of the day. We'll see. I only have to deliver it once today, so that's a good thing. All right? So anyways, I'm going to go ahead and pull up the PowerPoint. We'll get started. What I do need for you guys, or from you guys, is your total undivided attention. Okay? And the reason I am absolutely demanding your undivided attention today, there we go, is that the skill that we are learning today, which is how to write an electron configuration using the periodic table as a guide, this skill is absolutely fundamental to your success for the entire year, okay? If I had to make a top 5 list of the 5 most important things that you should walk out of this classroom with at the end of the year, what we're doing today is one of those things. Does that make sense? You have to understand how to write electron configurations, and you have to be able to do it with nothing but the periodic table as your guide, okay? I can't continue to provide you with boarding houses that are modified as needed to be able to write the electron configurations, because our boarding houses have to start getting pretty darn big, okay? So you have to learn how to do it using the periodic table, all right? And I would also put up there on that top 5 list mole-gram conversions, which is something that we learned in our last unit. So how to convert from grams to moles and moles to grams, that is a concept that will keep coming up in unit after unit after unit, just like electron configurations and valence electrons, which is what we talk about in this module. Okay, it just keeps coming up over and over and over. And if you understand it, it is a very, very powerful tool for you to be able to do lots and lots of things and answer lots and lots of questions. Okay, so today is not the day to be distracted with your cell phones, all right? To be checking on, baseball scores, basketball scores, ice hockey scores, whatever's going on. It's not the time to be Instagramming and all those other things. I just need your full undivided attention. So can you do that for one full class period today?
Yeah.
Okay? I know Luca is doubting me right now. He's like, I don't know. You're really asking a lot of me right now. He knows I'm talking directly to him. Okay, so you guys, if you look, first slide in the PowerPoint is just me sort of giving you the overview. Have y'all ever heard the phrase like when you write an essay, tell them what you're going to tell them, and then at the end wrap it up by telling them what you told them?
Yeah.
Has anybody ever heard that? That's what a good essay is supposed to be. Okay? Your introduction, you tell them what you're going to tell them, foreshadow. Then your body of your paper, you tell them, give the evidence. And then at the conclusion, the last body, paragraph, whatever, is you tell them what you told them. All right? That's it. That's how my dad explained writing essays to me when I was in high school. And I was like, oh my God, that's so amazing. And I've used it for the rest of my life. So that's a good skill. All right? But we are going to be we're going to be going back and talking a little bit about the Bohr model of the atom, but also talking about how that overlaps with the electron cloud model of the atom. Okay? So we're going to see really the marriage between those two models. Because the last POGL that we did last week was on electron energy and light. That was to help you fully understand the Bohr model of the atom, the electron shell model of the atom. We're not going to abandon that electron shell model of the atom. We're simply going to update it, revise it, add in new information, which is this electron cloud model of the atom, okay? And then what we're going to be learning how to do today is write electron configurations using nothing but the periodic table as your guide. We're going to focus today on doing that just for neutral atoms. Okay? I don't think today that we're going to get into ions. That'll be something that we wrap up in another class period. And hopefully today we will also get to that concept of valence electrons. I know that that's not a completely new term for most of you. Most of you were introduced to the definition of valence electrons when you were in physical science. So it's not a completely new concept, but we're going to talk about how to get those numbers using your electron configurations. Okay? All right, so do you guys remember Bohr model of the atom with an atomic nucleus and all of those rings that surround the nucleus? It might seem like for years you guys have been drawing these things where you've got a nucleus in the middle and you had the first ring, and you guys at some point from some teacher were probably told, don't ever, ever, ever put more than 2 dots or electrons on the first ring that surrounds the atomic nucleus. Has anybody ever heard that rule before? That is still true, and today we're going to learn why, okay? And then in the second ring, the next big ring surrounding the nucleus, a little bit farther away from the nucleus, a little bit higher in energy, you guys learned that you could put up to how many electrons there? 8. You guys were taught you can put up to 8 dots on that ring, okay? And again, today, we're going to learn why. And then in the third ring, how many of you were ever taught that the third ring, you could only put 8 electrons there? Did anybody ever learn 2, 8, and 8? Okay, well, that's not true, all right? It is not true that you can only put 8 in the third ring, all right? But your teachers were not completely lying to you, all right? They were simply stopping at a certain point on the periodic table and not asking you to go beyond that. All right? We are going to go beyond that. So what you're actually going to learn today is that that third ring can actually hold up to 18 electrons instead of 8. And again, we're going to talk about why. So by the end of this class period, you're going to know why it's 2, 8, and 18. And then the fourth ring can actually hold up to 32. We're going to answer all of those questions. All right? Next slide. So now you guys, let's talk about the definition of an orbital. Okay? Rather than thinking of electrons as residing in permanent shells, and we need to stop for just a second and talk about all the synonyms that people use for shells. Okay? You might hear a shell referred to as a ring around the nucleus. You might hear it referred to as a shell, but what it really corresponds to is the energy level those rings or shells are the energy levels. They're telling you something about how much energy an electron has. And if that ring is closer to the nucleus, then we would say that the electron is low in energy. But if that ring is farther away from the nucleus, like the third, the fourth, the fifth ring, we're talking about a ring or a shell far away from the nucleus that has high energy. So the bigger the ring number, the higher the energy of the electron. Okay? So within each one of those rings, we have electron clouds. So now we're getting into that Schrodinger model of the atom. So Schrodinger does not say that rings don't exist, but instead Schrodinger gives a little bit more detail regarding the composition of those rings. And what he says is that those rings consist of electron clouds or orbitals. They are regions, three-dimensional regions of space that surround an atomic nucleus, and they're places where electrons are, quote, most likely to be found. Three-dimensional regions of space surrounding an atomic nucleus where an electron is most likely to be found. So the way that I worded that up there, I called it regions of high probability. That means most likely to be found, okay? Where a given electron is found, and look at that last statement, based on its energy. So in other words, the type of cloud also tells us something about the energy of the electron. Not just the ring that it's in, but the cloud that it's in as well. Tells us something about the electron energy. Okay? So that is the definition of an orbital, which is another word for an electron cloud. So you guys, orbitals are nothing more than electron clouds. And those clouds are three-dimensional regions of space surrounding the atomic nucleus where the electron is most likely to be found. Okay? Now, these orbitals are sometimes referred to as sublevels. Okay? You guys, this is where chemistry can get a little bit confusing because they have so many different words that mean the same thing. Does that make sense? All right? So an electron cloud is the same as an orbital, which is the same as a sublevel. Okay? Do you guys remember the boarding house model? So we had a house like this, and we had the first floor, the second floor, and the third floor. Are y'all following? You guys, the floors were Bohr's rings, the energy levels. So the first floor is the first ring that surrounds the atomic nucleus. The second floor is the second ring that surrounds the atomic nucleus. And the third floor is the third ring that surrounds the atomic nucleus. But if you remember from that boarding house model, there were different types of rooms on these floors. And the first floor only had what type of room?
Sunny.
The sunny room, okay? So right here on that first floor, we had a sunny room. And over here, if you remember the model, we had it labeled the kitchen. And nobody would sleep in the kitchen. Y'all remember that? Okay? And then on the second floor, we had the sunny rooms, and what else? The pink rooms. So we had the sunny rooms and we had the pink rooms. And then on the third floor, the sunny rooms, the pink rooms, and then the model stopped there. Okay? And you can use those models to generate electron configurations, but it stops working for you when you go above, essentially, ring number 4 and the sunny room. Like if we drew a fourth floor on here and then the sunny room and the pink rooms, all right, it starts to fall apart unless we dramatically start to alter the composition, how many rooms and what types of rooms are available in that boarding house, okay? So, you guys, the floors were the energy rings, the levels, the shells. The rooms, you guys, were the sublevels. In other words, the rooms really were the orbitals, the electron clouds. And the reason why it was sunny room and pink room, you guys, the sublevels or the orbitals, they are represented by letters of the alphabet. And those 4 letters of the alphabet are S, P, D, and F. In other words, the sunny room was representing the S orbital. Am I making sense? And the P orbital was what was the pink room. Are you guys following? Okay? But what you notice is in this boarding house model that we looked at, we're only talking about S and P. It doesn't have something in there for D and F. So we would have to really change this boarding house model to start to incorporate all of the different electron clouds that are truly available for elements in the ground state. Am I making sense? Okay? All right. Okay. So, the types of orbitals. I've already given you a little bit of a preview. The 4 different orbitals are labeled with letters, and we call them S, P, D, and F. That first orbital or electron cloud or sublevel, all of those mean the same thing, is the S orbital. S for sphere. The S orbital has a spherical shape, okay? A perfectly symmetrical spherical shape, all right? These are the lowest possible energy orbitals that exist in any energy level. Do you guys remember the manager had a little bit of OCD and he had very specific guidelines for how he placed the borders in the boarding house? Does anybody remember that? On any floor, when the manager was putting borders into the house, where did he always put the borders first?
The bottom one.
He put them on the bottom bunk of what room? The sunny room. He always put the borders into the bottom bunk of the sunny room first. The reason why? The S orbital is the lowest in energy. And we always put electrons into lowest energy electron clouds first. So even when he got to the second floor and he had the option of the sunny room versus the pink room, he still always put the borders in the sunny room first. In other words, the S orbital, okay? Now, we also, in this analogy, these rooms were filled with bunk beds. Do y'all remember that? Well, the sunny room had how many bunk beds?
One set.
Okay, only one bunk bed. So go here, get rid of this, okay? And there was one bunk bed. And one bunk bed could hold how many borders?
2.
2. And we would put them on the bottom and then the top, okay? So there was a maximum of 2 borders per bunk bed. Do y'all remember that? All right? You put one person on each mattress, all right? Well, you guys, an electron cloud, any single electron cloud can hold a maximum of 2 electrons, all right? That's why they chose the bunk bed analogy, because the bunk bed can hold 2 people. So, the S orbital, the lowest energy orbitals that exist, they are spherically shaped and can hold a maximum of 2 electrons. Now, before we move, I want to show you something. If I stand here, or if I stand here, or if I go back in that corner, or if I go back in that corner, does that sphere look different regardless of where I stand in the room?
No.
It looks exactly the same, no matter where I stand in the room. We say that the S orbital has one spatial orientation, meaning that no matter where I stand, it always looks the same, okay? So that S orbital has one spatial orientation, and that one spatial orientation can hold 2 electrons. Now, do you guys notice that that sphere is oriented along a set of 3-dimensional axes? Do y'all see that? There's an x-axis, a y-axis, and a z-axis. So if we were thinking about math, you guys, our x-axis we always have as our horizontal axis, and our y-axis is our vertical axis. Well, in 3 dimensions, we have a third axis, which is our z-axis, that comes straight out in front of us and goes straight behind us. Literally, that would bisect our body. So that would be the z-axis. So that sphere is perfectly situated around the origin of those three axes. In other words, when I say the origin, I'm talking about coordinates 0, 0, 0. Now, you guys, at coordinates 0, 0, 0, I never find any electrons. Why? What does that set of coordinates 0, 0, 0 represent in our atom?
The nucleus.
Perfect. It represents the atomic nucleus. And we never find electrons in that atomic nucleus. Is everybody with me so far? Awesome. Let's get to the next one. You guys, and you can do there you go. So, the p orbitals is our next set of orbitals. Just like in our boarding house, after the sunny room, we had the pink room. The pink room represents the p orbitals. Now, in our pink room, how many bunk beds did we have? We had 3 bunk rooms, or bunk beds, excuse me. So in our pink room, 3 bunk beds. So over here, there's bunk bed, bunk bed, bunk bed. Okay? You guys, that is because the p orbitals have what we call 3 spatial orientations. So a bunk bed is a spatial orientation. All right? So these p orbitals, they're higher in energy. Notice you don't see a p orbital until after you see an s orbital. The p orbitals are higher in energy than the s orbitals. Their shape, I was always taught the words dumbbell or figure 8 or infinity symbol. All right? Miss Smith said she likes to use the word peanut shape because you know a peanut is like bigger at the ends and smaller in the middle. It's the same idea. Okay? What's that? Well, kind of like 2 jelly beans stacked together. Yes. Okay? The reason she likes peanut is at least it gives rise to the letter P. Just like pink room gave rise to the letter P. Does that make sense? Okay? So the p orbitals, they're higher in energy than the s orbitals. They're shaped like peanuts, dumbbells, figure 8s, etc. And these guys are actually situated along the axes. And therefore they look different depending on which axis you're on. So there is a p orbital that is situated along the x-axis. There's a p orbital that's situated along the y-axis. And then there's a p orbital that's situated along the z-axis that comes straight out at you. So we call that 3 spatial orientations, or 3 clouds. But every cloud can hold how many electrons? Just like a bunk bed. 2. A bunk bed can hold 2 borders. A cloud can hold 2 electrons. So if you guys remember in our pink room, we would take a border and we would put it here. Well, let me fill up this guy first because that wouldn't happen. Okay? We would put a border here, and then a border here, and then a border here. Do y'all remember that?
And then
we would go back and occupy the top bunks like that. Okay? But ultimately, what you found is in that pink room, you could never get more than 6 borders. The borders are the electrons. So the S sunny room, 1 bunk bed, could hold 2 borders, aka 2 electrons. The pink room, 3 bunk beds, 2 borders each. That is a total of 6 electrons. Okay? So those are our p orbitals. Everybody good so far? Okay? Now, the next set of orbitals is the d set. Nope, go back. There we go. Okay? D orbitals. Okay? You guys, our d orbitals. Okay? You can already see based on the pictures in the slide that we've got 1, 2, 3, 4, 5 different spatial orientations for the d orbitals. And in case you're a pattern matcher, you should start seeing a pattern here. We had 1 bunk bed, 3 bunk beds. We're missing a set of rooms here that would represent the d orbitals, but how many bunk beds would be in a room that started with the letter D? 5. 5 spatial orientations, so 5 bunk beds. But every bunk bed, spatial orientation, can hold how many electrons? 2, and 5 times 2 is 10. So these d orbitals can hold a maximum of 10 electrons. So we've got 1 for 2, 1 spatial orientation, 2 electrons, 3 spatial orientations for 6 electrons, 5 spatial orientations for 10 electrons. You can now see the pattern. Our next cloud, which is the f orbital, goes up to 7 spatial orientations. And every spatial orientation holds 2 electrons, and 7 times 2 is 14. So, if I were to continue to use this boarding house model, I'd have to modify the house. What I would have to do is come out here, something like this. Okay, here's my first floor, there's my sunny room, there's my kitchen, okay? My second floor, like this, keep going like this, whoops, sunny room, and then don't forget about our pink rooms. Here's our pink room, right there. For the d orbitals yesterday, my students suggested, I said the dark room for D, but one of my students came up with a better idea and said, I think those should be the dance party rooms. So we're gonna have our little dance party rooms over here. Dance party room. There we go. And now it starts with D. And how many bunk beds are gonna need to be in those dance rooms? 5 bunk beds need to be in the dance rooms. Are y'all following? Okay? Now, can you go back to that d orbital slide for a second? Okay? You guys, we were trying to come up with a word that describes the shapes of those electron clouds for the d orbitals. Something that started with D. And I've got something different from every class so far. So yesterday, my 1A class said, well, those look like eggs in a carton. And so somebody said, how about dino eggs? So they said, those are dino eggs, and they're in there, dozen eggs, you know. So they're like, that's the dino eggs. And I'm like, okay, that works, D. All right? But then my 2 other classes, second block and third block yesterday, they apparently were hungry, and so they said, these are donut holes. And so they preferred the donut hole for the D analogy. And they said, in fact, you know, here's a set of 4 donut holes, and over here, you got the donut holes and the donut. They liked that. So whatever works for you, just keep it, okay? If you like dino eggs, if you like donuts, whichever one, d orbital, dino eggs, or donuts, okay? But then our f orbitals, you guys, these are the highest energy orbitals that exist. So S is the lowest, P is a little bit higher, D is actually a lot higher, and F is higher than that. So if I were like writing them like this, I would go like S and P and put those P above S, but just a little bit closer together. And then I would go D and F, like that, okay? There's a big leap between the pink room and the dance party room, okay? Big leap. The F orbitals, the highest energy orbitals that exist. You've already seen 7 possible spatial orientations, 2 electrons each, for a total of 14. And if we go to that picture, you guys, in my opinion, these start to look like flowers. Okay, so for me, that's where the letter F is. All right, so we've got the flower-shaped ones, and I always, in the previous like D model thing, go back. It's okay. No, right here, you guys. Do y'all notice that these 4 look very similar, yet this one up here is different? I always called this guy the ugly duckling. Okay, if you know the story of the ugly duckling from when you were a kid. All right. And so then when I get to the F orbitals and I've said these are the flowers, I said this guy was the offspring of the ugly duckling because he looks just like that. He just has 2 donut rings instead of 1. All right? All right, so feel free, thank you, to resume. So anyways, you guys, here's a summary, okay? Now, exactly, yesterday, I kept having students who were like, Ms. Karpovich, are you aware that your slide is upside down? And I'm like, yes, actually, I am. I did that on purpose. Okay? Every slide that I find that summarizes the S, the P, the D, and the F orbitals, it always starts with the S on top and it works its way down to the F. I hate that because it's the exact opposite of their energies. The S is lower in energy than P. The P is lower in energy than D, and the D is lower in energy than the F. So I just took my favorite slide that summarized all of the different clouds and turned it upside down so that it would reflect the relative energies. Does that make sense? So if we call S the lowest energy orbital number 1, then F would be the number 4. Something like that. Okay, so there's our summary. S, 1 spatial orientation, 2 electrons. P, 3 spatial orientation, 6 electrons. D, 5 spatial orientations, 10 electrons. And F, 7 spatial orientations, 14 electrons. Okay, so now, you guys, let's go back to that electron shell for model of the atom. 2 in the first ring, 8 in the second ring. Why do you think that the first ring can only hold 2 electrons? It does have the lowest amount of energy. You are not incorrect. There's more. Matthew?
Just the sun.
Exactly. Go back to your model over here, the boarding house. The first floor only had what type of room? The sunny room. And so if I look at that Bohr model of the atom with my rings, okay, so here I'm just going to do a little plus. That's my atomic nucleus that's positively charged. Here's that first ring, and we said it could hold 2 electrons. Well, folks, that's because the first ring only has the s orbital. The first floor only had 1 sunny room. But then I go to my second ring. Why were you always taught 8 in the second ring? 6 plus 2 is 8. And where do I get 6 plus 2? The sunny and the pink. In other words, the s orbitals and the p orbitals. Okay? Now, you guys, you were only taught earlier third ring 8 electrons. But that's because your teachers were only talking about elements that occupied the sunny rooms and the pink rooms. But, you guys, the third ring should also have what?
The dance party.
The dance party rooms, which corresponds to which orbital?
The D room.
The S, the P, and the D. So our third floor should really have sunny rooms, pink rooms, and dance party rooms. Okay? Because where do I get 18 from?
2 plus 6 plus 10.
2 plus 6 plus 10 is 18. And then, as I told you earlier today, I get out here to this fourth ring, and I told you guys earlier that the fourth ring could hold a maximum of what?
32.
32. Where does 32 come from?
2 plus 6 plus
2
10
plus 6 plus 10 plus
7.
14. Exactly. 7 orientations, 2 electrons each. That's where your 32 comes from. I told you that by the end of today's class period, you would know where the numbers on the rings came from. Does everybody understand that now? Okay? Is everybody anybody having like little aha light bulb moments right now?
I am.
Okay. Thank you, Luca. All right, next. You guys, I want you to look at this particular diagram. And I am going to come and draw for just a second. Okay? On my Promethean board. Okay. You guys, we said first floor, first ring, what types of orbitals?
S.
S, which has what shape?
Sphere.
Okay. There's my atomic nucleus, you guys. There's my 1s orbital. The sunny room on the first floor. Then I go to the second floor, which is higher in energy, farther away from the nucleus. So here's
Mr.
my
Peanut.
2s. Do y'all see the 2s?
Yeah.
It's still spherical in shape, but it's larger. You see that? Now, in my second floor, I don't just have the sunny room, I also have the pink room. Well, I've got 3 orientations. Okay, there's 1, there's 2, there's 3. There's all of my 2p orbitals. Okay? Then my second ring or floor of the boarding house is full. So I start moving to the third ring. And in the third ring, What was the first bedroom that got occupied?
Dino egg.
The S. Okay, the sunny room. So that sphere right there would be my 3s orbital. It's still spherically shaped, it's just larger. Y'all see that? Okay? So the shapes of the electron clouds are the same, but as you go out to higher and higher rings, the shapes just get bigger. Does that make sense? All right? And they all exist and overlap with one another. All right? Great job. Okay. Whoops. Just do X out. If you just push that X. There you go. Okay. So now, you guys, last class, we learned how to use the boarding house model or the orbital diagram model to generate an electron configuration. And so the output that you were supposed to finish on was to write out the atomic numbers 1 through 20. You were supposed to identify the element name, and you were supposed to write out the corresponding manager's code, aka electron configuration. Am I right? Okay? So, that's where we left off on Tuesday, for you guys Tuesday. All right? But what I said at the beginning of this class is that our model starts to fall apart and become less useful when we go to an atomic number that is above 20. Okay? And the reason why is as we go through numbers 1 through 20, the only types of rooms that we need in our boarding house are the sunny rooms and the pink rooms. But as soon as I go above an atomic number of 20, I need to start opening up those dance party rooms. And that was not in the original model that you were given. Does that make sense? And we don't want to just keep building this house with all of these additional sort of bedrooms and bunk beds and so forth and so on. Okay? So that is why today we're learning how to use the periodic table as our guide instead. Okay? So, next, you guys, we're going to prepare our periodic tables for our new adventure. Okay? The rules for these periodic tables, you may only write on them something that I tell you to write on them. Okay? You do not take notes on these sheets, meaning the periodic tables. You do not do your example or sample electron configurations. You do not write on here any kind of notes from the PowerPoint, like what are all the pieces of the electron configuration. Okay? It is simply a tool. Therefore, number 1, you may write your name on this. So please put your name, maybe the upper right-hand corner of that periodic table. Number 2, I already asked you guys to get 4 different colored pencils. If you have highlighters and you would prefer to use those, or markers, or crayons, knock yourself out. What I have here is colored pencils. Okay? What you're going to do is you're going to choose a colored pencil to represent the letter S. Another different color is going to be used to represent the letter P. A third color will represent the letter D. And a fourth color will represent the letter F. So a color for S, a color for P, a color for D, a color for F. So the first thing I want you to do after putting your name on there is choose which one you want to represent which letter, and just make a key or a legend on your periodic table. Some people literally just take the color and write the letter S. Some people like to actually do boxes and then say this is S. Whatever you want to do. So create a legend or a key so that you know which color represents which letter, S, P, D, or F. Okay? Okay? All right. And one more. Okay. So you guys, notice up here, I've got a sample periodic table, all right, that shows you how you're going to be coloring, you're literally coloring your periodic table, all right? So I told you that these colors were going to represent the letters S, P, D, and F. Okay, you guys, the S block of the periodic table The S block of the periodic table is vertical column 1, vertical column 2, plus the element square for helium. Yes?
Should we like color it in? Or should we just, like,
That's up
gloss
to
it?
you. You can either outline it, color it in. Different students like to do different things. I'm okay with either. Okay? So again, your S block, vertical column 1, vertical column 2, plus the element symbol for helium, the square. In other words, you guys, it is literally as though we plucked out the element square for helium and put it right over here next to hydrogen, so that it is part of what we call the S block. The sunny room portion of the periodic table. Okay? After your S block, your P block, everybody, your P block is vertical columns 13, so it starts right here at vertical column 13, vertical column 14, 15, 16, 17, and 18. So the P block is vertical columns 13 through 18, except the square for helium, which you already colored in for what block? S. Okay? So the S, 1 and 2 plus helium, the P, 13 through 18 minus helium. Then you guys, the D block is vertical columns 3 through 12. So the D block is the bridge between the S and the P. Okay? And then finally, your F block is these 2 rows of elements down here at the bottom of the periodic table. The 2 rows of elements that are off all by themselves. All right? They got kicked off the island, banished, so they formed their own little country. That's your F block, down there at the bottom of the periodic table.
Texas was a country. And independent.
So S, P, D, and F.
So the whole entire bottom is
Or this too.
Correct. Correct. Correct.
I see.
So
It's okay. Yeah, don't worry about it. Because if you look at that one, it's different than that and that. Because like they, but basically the same rules apply. So like this would continue down here. So those 3 would be part of the D. Does that make sense? And then over here, these 6 right here would be part of the D. Okay?
D is
Why are there just a few that just don't get friends? There are a few that just don't get friends. It's not actually good.
So I think Kelso is noticing the squares that have no element symbols in them. Is that right?
Yes.
Yes. So if you look at the periodic table that I have on the wall, those have actually been filled in with the symbols and names of the elements that have been more recently discovered. Okay? And the same trend applies. So vertically, if you go down 3 through 12, that still would be part of the D block. And then vertically, 13 through 18 would still be part of the P block. Does that make sense?
Can
We
imagine.
really use the same colors.
So if you want to color in those blank ones, feel free. It doesn't matter.
This is blue. Here's not. Yes, that is she. We pick the colors.
That's really.
Literally just pick them. These boxes up first.
Yeah, she looks kind of tired.
Miss Laura. Miss Laura was a great
yeah, the only advice is just
You did get that was nonsense.
6th grade. So Yes.
Seven.
It is.
Yes. So no, all of those are F, and these two right here are D.
She's moving.
Okay,
Where are you going?
so I do need for us to wrap up the coloring. I know everybody loves coloring, or at least a lot of people do.
But Mom.
I find my students get the most peaceful when they are sitting and coloring.
That's terrible.
Perfect, that looks great.
Wait. Where's NA?
Okay, so you guys, while you're finishing up your coloring, I'm going to talk a little bit about the basics of the electron configuration. And this should make sense to you guys if you remember what we did on Monday. Okay? So, electron configurations. What I have up on the PowerPoint, 1S1, is the electron configuration for the element hydrogen. If you remember last time, we talked about the manager's code for how the borders were listed in the boarding house. And the manager's code consisted of some set of coefficients, letters, and superscripts. Do y'all remember that?
Yes.
So it might have been, for example, 1S2, 2S2, 2P6. But it was a set of coefficients, letters, and superscripts. So that is the electron configuration. Okay? So what we have here in 1S1, we've got the coefficient 1 right here. Okay? And that coefficient, if you look up there, it says this corresponds to the energy level or the ring that the electrons are located in. So the coefficients represent the shells. Do y'all remember that? Okay? So these are your shells, rings, energy levels. Okay? In the boarding house model, you guys, that was what floor the borders were on. Am I making sense? Whether they were on the first floor, the second floor, or the third floor. Okay? What you guys are going to find out with your periodic tables today is that that coefficient will correspond to the horizontal row number. If you look at your periodic tables, the vertical columns are labeled with numbers 1 through 18, and you will find that the horizontal rows are labeled with the numbers 1 through 7. Those coefficients are going to correspond to horizontal row numbers. Okay? Next, you've got these letters. The letters you should now know can be either S, P, D, or F. With the boarding house model, we only saw S and P. But today, we're going to start seeing things that have D. Okay? And then eventually we'll get to some that have F. So, these letters, like this, S, in the boarding house model, that was the type of room they were in. In other words, was it a sunny room or a pink room? All right? But what we now know is that that is equal to the shape of the electron cloud that the electron is located in. Whether it's a spherical shape, whether it's a peanut shape, whether it's the donut hole shape. Okay? So the letters tell you the shape of the electron cloud, which also tells you something about the relative energy of the electron, whether it's low or whether it's high. If it's in an S, it's very low in energy. If it's in a P, it's a little bit higher in energy, so forth and so on. Okay? And then lastly, and you guys, with the periodic table, I should have mentioned, those letters are now going to correspond to the colored blocks on the periodic table. Whether you colored S, P, D, or F. So those are the letters. And then lastly, we've got these superscripts up here. Okay? 1 or 2 or 5 or 6. Okay? Your superscripts, actually, in the boarding house model, they represented the number of boarders. Do y'all remember that? Okay. The number of people that were renting out rooms. For us, you guys, this represents the number of electrons in that cloud. The number of electrons that are in the cloud. Okay? And what you're going to find on your periodic table is that that number corresponds to the number of element squares in that block. That you had to cross to get to your element. Okay? So the number of element squares in that block that you had to essentially go over to get to your element. Okay? So, that's the basics of electron configurations. Luca.
So why is it for the superscript just like really what?
Well, that's a great question. That is a great question. What I will tell you is the sum of these superscripts is the atomic number. So for example, what I said when I started this was that this was the electron configuration for hydrogen. The atomic number for hydrogen is 1. So the superscript is 1. Okay? When I look at the electron configuration for helium, which you guys wrote out, it's 1s2. Well, the superscript is 2. The atomic number of helium is 2. The electron configuration, if you did lithium using the boarding house model, would be 1s2, 2s1. Well, the sum of 2 plus 1 is 3, and the atomic number for lithium is 3. So the sum of the superscripts will equal the atomic number. Okay? Caitlin?
Wait, but how is it the element squares in the block?
I couldn't hear you. How is it? What?
the number of element squares in that block?
You'll see as we start using the periodic table.
Okay.
It's not all going to make sense until we actually start talking about it. Okay? Yes,
Yeah,
Luca.
back then.
Yes.
Oh, so you're saying like,
Is this a
because you have multiple, like if you're in the F block, you have 1s2 in there, and then you just add all those people.
All right. So, you guys, we've got to have, do y'all remember the manager's rules? He was very OCD about how he put the borders into the bedrooms, into the bunks, etc., etc. We have to have rules too for using our periodic table. Okay? So, number 1, the start position. This should be on the back of your first page of guided notes. You just have to fill in some blanks. The start position is always in front of the element hydrogen. When I'm doing this, I like to pretend like my periodic table is a board game, like Candyland or something like that, Monopoly, okay? And so in a board game, there's always a start position. Our start position is right over here in front of hydrogen, okay? So in other words, at coordinates 1, 1, okay? Start position is in front of hydrogen. You guys, the element squares are your spaces on your board game. I like to call them steps, like I'm walking across the board game. Okay? So this is 1 step, this would be 2 steps, etc. So your element squares are steps or spaces in the board game. Okay? That you move forward. Third, follow the atomic numbers. You can never skip steps or element squares. I can't jump from 1 to 26. I have to go over all the atomic numbers between 1 and 26 to get to element 26. So you have to follow the atomic numbers. Okay? Next, every time we enter a new block, and by block I mean S block, D block, P block, every time I enter a new block or a new horizontal row, 1, 2, 3, 4, 5, 6, 7. Every time I enter a new color, block, or a new row, horizontal row number, I'm going to start recounting my steps from the number 1. So if I'm going across horizontal row number 1, I would go 1 step, 2 steps. But if I go down to horizontal row number 2, I start back at the number 1 when I'm counting steps. And then this would be 1, 2, 3, 4, 5, so forth and so on. Okay? But I actually just violated my rule because that was a new block. So 1, 2, new block, 1, 2, 3, 4, 5, 6. Like that. Okay? Every time you enter new block or new horizontal row, start recounting the squares from the number 1. Okay? Next, the superscript for the letter S can never go above 2. The sunny bedroom. How many bunk beds were in the sunny bedroom? 1. One bunk bed could hold how many people?
Doves.
2. The S orbital cannot ever hold more than 2 electrons, period. So the superscript can't go above 2 if the letter is S. Next, the superscript for the letter P cannot go above 6 because the pink room had how many beds?
3.
3 bunk beds. Each bunk bed could hold 2 people. 3 times 2 is 6. So the superscript for the letter P can never go above 6. And then for D, it can't go above 10. And for F, it cannot go above 14. The maximum number of electrons that can go in those orbitals. Okay? Next. All right? When we cross over the S and P blocks, so when I cross over the S block right here, the S block right here, or the P block right here, when I cross over the S and the P blocks, the coefficient that goes in front of the letter is going to be equal to the horizontal row number on the periodic table. Okay? Those horizontal rows are called periods. Next, when we cross over the D block, so here's my D block right here. If I'm going through the 4th ring, energy level, row, right here, over 19 and 20, I'm in the 4S. But as soon as I hit scandium, I enter the D block. This right here is not 4D. It is actually 3D. You take the horizontal row number and you subtract 1. So the coefficient for whatever you put in front of the D orbital is always the horizontal row number minus 1. I promise you this will make sense when we actually start doing examples. Okay? Then, when we cross over the F block, the coefficient that goes in front of the letter F is equal to the horizontal row number minus 2. Okay, minus 2. Again, follow the atomic numbers. Do not violate that rule. If you do, you will mess up. All right, so let's practice. Okay? You guys, you now have on your practice worksheet page. So go to that last page in the packet that you picked up today. All right, this is our practice. You've got a table, section 1. Does everybody see where it says section 1? Elements. Okay? Yes?
Yes.
Okay. Miss Mahoney, will you turn the camera so that it's facing this right now?
Yes.
Okay. So, you guys, we're going to pretend like at the moment that we have never seen the boarding house model or the orbital diagram model. And instead, all we have as our tool is the periodic table. So we've got our colored periodic tables in front of us. We have positioned ourselves so that we're over here. Start position is front of hydrogen. And it's like we roll the dice and we get the number 1. You guys, whatever I roll on the dice is equal to the atomic number. Atomic number represents what? Number of protons. And for a neutral element, number of protons always is equal to what? The electrons. So the atomic number is also the number of electrons for a neutral atom. So for hydrogen, that's 1. Okay? So in other words, I want to move from my start position over to element square number 1. Is everybody following? But when I enter and go from start to element square number 1, what horizontal row number did I just enter?
1.
Horizontal row number 1. So I'm going to write the coefficient 1. Okay? Next, what colored block of the periodic table did I just enter?
S.
The S block. So I write the letter S. And then from start, how many squares forward did I move to get to atomic number 1? 1. That's my superscript. And we read that 1s1. That is the electron configuration for hydrogen. Just like, now think about your boarding house model. When the manager was putting boarders into the boarding house, he always filled up the first floor, sunny room, lower bunk bed first. And so he would write coefficient 1 for the floor, letter S for the sunny room, superscript 1 for the number of boarders in the bunk bed in the sunny room. Okay? So our electron configuration is 1s1. Now, the crappy thing about this game is that we keep getting thrown back to start. So it's like Monopoly where you pull the chance card that says return to start. Okay? So we're going to go back to start, roll the dice again, and this time we're going to get the element 2. So we roll a 2. So we need to move from start to atomic number 2. So as I move from start over to atomic number 2, what horizontal row number did I just enter? Horizontal row number? 1. So I'm going to write a 1 right there. Okay? When I cross over those 2 steps, okay, are they the same color?
Yes.
Yes. And they represent what block of the periodic table?
S.
S. So I draw the letter S, and I only draw it one time because they're the same color. Okay? And then, how many element squares forward do I move from start to get to atomic number 2? 2. So my superscript is 2. Okay? So the electron configuration for helium is simply 1s2. All right? Next, we've got lithium. We go back to start, we roll the dice, we get a 3. Lithium's atomic number is 3, which means it has 3 electrons for a neutral atom. All right? But I can't just jump from start down to atomic number 3. I have to cross over squares 1 and 2 before I can get to square 3. So, to cross over squares 1 and 2, what's my horizontal row number?
2.
No. 1 is the horizontal row number to cross over squares 1 and 2. So, horizontal row number 1. To go over squares 1 and 2, what colored block am I crossing? S block. To get to the end of that S block in that row, how many element spaces forward do I move? No. 2. To get to the end of that row, S block, I go forward 1, 2 spaces. I'm now right here. Now I need to move from square 2 to square 3. I'm following the atomic numbers. But as soon as I move from square 2 to square 3, I've entered a new horizontal row. What horizontal row have I just entered? 2. So I draw the big coefficient, 2. What colored block did I just enter? S. And in this row, how many squares forward did I move to get to lithium? Just 1. Okay? And you guys, remember the question that Luca asked earlier? I said if you add together the atomic, or the superscripts, 1 plus 2, it equals the atomic number for the element, 3. If they don't, you've done something wrong. Okay? And you guys, this goes with our boarding house model. When I was filling up the boarding house, okay? So here's my boarding house. Here was the first floor. I had the sunny room, and I had the kitchen. Y'all remember that? And then the second floor, I had my sunny room, and I had my pink rooms. But remember, he fills up the sunning room on the first floor first. You guys, the sunning room on the first floor, if that gets filled up, it's 1s2. And then I go to the second floor, and I put people into the sunning room first. So for lithium, that's second floor, sunning room, but only one border. Am I making sense? All right? Now, you guys, I'm going to jump. Okay?
You got you.
I'm going to jump to nitrogen. All right? So buckle your seatbelts. Fasten your seatbelts. All right? Because I don't want to lose anybody. I don't want you falling out of your chairs. What is the atomic number for nitrogen?
7.
7. So the atomic number is 7. So that means that nitrogen has 7 protons, which means that nitrogen has how many electrons?
7.
7. So we've got to map out the location of 7 electrons, aka borders. Okay? But I go from start position. Always from start position, always follow the atomic numbers. So from start, the first horizontal row that I have to cross over is horizontal row number what?
1.
1. So I'm going to write a 1. What block?
S.
S. How many spaces or steps or squares across to get to the end of that block or the end of that row?
2.
2. So that's my superscript. Then I move from 2 to 3 squares. Square 2 to square 3. I enter what horizontal row number? 2. What block?
S.
S. To get to the end of the S block, how many element squares do I cross?
2.
2. The sunny room gets filled up anytime there's 2 borders. Are y'all following? But then when the sunny room gets filled, now we can start placing electrons where? On the second floor, the P block. The pink rooms. You guys, so right now, I'm sitting right here. I now need to travel across. I'm still in what horizontal row number?
2.
2. So I'm going to write the big number 2. But I have now entered what block?
P.
P. Exactly. And in the P block, how many element squares forward do I move to get to nitrogen?
3.
3. Exactly. You guys see what I'm doing? Okay. Now, again, buckle your seatbelts. I'm going to take you down to iron. Okay? So let's go to iron. You guys, iron, atomic number 26. I just put y'all in a time machine. Okay? Iron, number 26. I have to follow the atomic numbers. So from start, I go over horizontal row number what? 1. What block?
S.
S. How many squares? 2. I then enter what horizontal row number?
2.
2. What block?
S.
S. How many squares?
3.
2. Then I go to what? I'm still in what horizontal row number? 2, but I've now entered a new block.
P.
P block. I go all the way across. How many steps?
6.
6. I now enter what horizontal row number?
3.
3. What block?
S.
S. How many steps?
2.
Then I zoom on over to cross over aluminum through argon. What horizontal row number?
3.
Still horizontal row number 3. What block?
P.
P. How many steps?
6.
Then I enter horizontal row number
4.
4. What block?
S.
S. How many squares to the end of that block?
2.
But then, you guys, we enter the D block.
Oh
And when I enter the D block, the energy level is no longer equal to the horizontal row number. It's the horizontal row number minus 1. So 4 minus 1 is 3. So now it's coefficient 3. What block?
D.
D. And how many squares into the D block to get to iron? 6. is correct.
So much.
Imagine
Yes.
having to do like this number of things.
She's so well groomed.
Yes. Yes. You've got it. Okay? Now, you guys, we've got 5 more minutes. You've been doing fantastic. Thank you, because I asked for your undivided attention today, and y'all have really done well. So I do appreciate that. Okay? But it does look like you guys are starting to see very quickly how to use the periodic table to write these electron configurations, which is awesome. Okay? So you no longer need the boarding house, which didn't have the D rooms and the F rooms. Okay? We've got our periodic table to use instead. Now I told you guys that if you added up the superscripts, what should it equal? Watch for iron. 6 plus 2 is 8. 8 plus 6 is 14. 14 plus 2 is 16. 16 plus 6 is 22. 22 plus 2 is 24. 24 plus 2 is 26.
Wow.
There is a built-in method for you to check your work. Check the superscripts. Do they add up to equal the atomic number? Did you make sure that the superscript for S was never greater than what? No, for S? 2. For the superscript for P, never greater than what? 6. Okay? And we haven't gone far enough yet, but the superscript for D cannot be greater than 10. And for F, 14. Allison.
So I'm just making sure
Because
that
that's
you
what
only like subtract 1 from the
Across the D block.
for the D block.
Yes.
So it can be like 4 2 squared.
4S squared.
4S squared.
That's where mine is.
3D, it can go all the way up to 10. But as soon as I come right here, it goes back to 4P. Don't worry about that yet. Don't worry about F yet. Elkie. Yeah, don't worry about F yet. Okay? Now, you guys, how are we doing?
Quite well.
Okay? I am going to tell you your homework is to take this table right here and just finish these long form electron configurations. But because we've got just a few minutes, I'm going to go ahead very quickly and show you about the concept of valence electrons. Okay? Because it's super simple. All right? You guys learned a long time ago, what is the definition of valence electrons? The electrons in what, Luca? The outer shell. Do y'all remember learning that definition?
Yes.
The number of electrons in the outer shell. In other words, you guys, it is the electrons in the highest energy level. In my electron configurations, which part of the electron configuration represents energy levels? Not the letter. That's the sublevel. The coefficient. The coefficient is the energy level. So let's look at hydrogen. What is the highest energy level, the only energy level for hydrogen? 1. Now, check the superscript, because the superscript is the number of electrons in that level. So, the superscript is 1. Hydrogen has 1 valence electron. Now let's look at helium. Helium's highest energy level was 1. What is the superscript for that energy level? 2. So helium has 2 valence electrons. But now let's look at lithium. Lithium's highest energy level is what? 2. It's this right here. Superscript for that? 1. Lithium has 1 valence electron. Okay, you guys. Nitrogen. What is nitrogen's highest energy level?
2.
But look closely. You've got this coefficient 2 and this coefficient 2. You have to add together all of those. So 2 plus 3 is 5 valence electrons for nitrogen. Let's look at iron. What is iron's highest energy level? 4, how many electrons are in that energy level? 2. The valence electrons for iron is 2. So you guys should be able to finish these long form electron configurations and the valence electrons. Has everybody got that? Okay, that's all you need to do for homework. And I will see you again next Tuesday. All right? Thank you again for your patience.
Oh wait, it's time to go.
Yes, have a great afternoon and a great weekend.
Oh my god.
Thank you so much.
I did that
Following student come to the front office. Julianne Wilson.
Is this a Is this just a blank copy you were working from? Okay, I gotcha. But what you would do here is this should be, convert this to a decimal, 0.78